Hello and welcome to part 2 of Dev Maths and Stats Refresher Course Lecture 2. In this lecture we look at how we actually find derivatives from first principles, meaning what's the logic behind the methods that we're going to use in the rest of the lecture and the rest of the course. So it's good if you can understand this, it helps you use the methods properly, but it's not totally essential, so don't worry if you cannot follow every single detail of why it works. So here, remember, when you see red stuff, that's when the Maple program is actually doing mathematical calculation, which is why we're using it. So if you have Maple, you want to follow this, it's important to go to the restart command and press that, and then it always automatically jumps to the next red one. So here that gives you some blue output, and it means that we have defined this function. So we're going to take this as our example function, and we need to be able to find the gradient of that for any value of x. That's what differentiation will let you do. This is a quadratic, so it's going to be a curve, so we need to be looking for the slope of that tangent. And just to start with, we're going to concentrate on the point just where x is equal to 2 to make it concrete. So it's taking x is 2, we want to find what's the slope of this curve, or what's the slope of the tangent. A good starting point is to know, okay, what's the value of the function at 5? What's the value of the function at x equals 2? So we substitute x equals 2 into this, and we find it 5. So you can put 2 into here, you get 5. Now here's a diagram looking at what we're trying to do. Okay. So the red thing is the function we're interested in. We've chosen the point 2, and I want to know what's the gradient of this graph here, and that's the same as the gradient of this green line here, the tangent. Now, it's difficult to see how we're going to do it because all we've got is the value of f of x at 2 is 5, so we have this height here. We can calculate that as 5, but we can't calculate the other things we need to know to work out a gradient, which are, we need some numbers here, and all we have at the moment is this height. We know this is 5, that's 5, but we don't know anything else. So let's see how we can go about doing this. Now, as some of those example visualizations show you, what you can do is approximate this gradient by drawing what's called a secant instead of the tangent. So we go along from here, we can go forward, for example, to x equals 4, to here, so 2 steps forward. At this point, we can calculate the value of f is 29 by doing this calculation, 29. If we plot that and join up the points, we have this. So, you know this is height 5, you know this is height 29 by putting in things into the function. So now we can work out that the run along here is 2 units, the rise up here, the increase in y is 29 minus 5 is 24. So it's going up 24, it went along 2, so the gradient is 24 divided by 2 is 12. So this black line goes up 12 for every unit, so the gradient is 12. And then the calculation I've done is, we need this for the next part, but this is, ignore this, this is a bit of internal Maple. This is the notation you need to understand the rest of it. But for f is the function, a is the points we're starting with, so here a is equal to 2, and h is the increase in x. So x is 2, or a is 2 here. H is the increase, so here it's 2. We're going along from 2 steps along. So this is showing the function at 2 plus 2, the function at 4 minus the function at 2. So that's the increase in the function. This is the increase in x. So this is the rise and this is the run, and it gives us 12. So we're going to keep repeating this. Okay, now this is an approximation to the tangent's gradient. Is the approximation too big or too small? So hopefully you thought for yourself, but it's clearly too big. That's too steep. We need to have this gradient here. Now, an obvious way of doing that is to make this h smaller. Instead of h being 2, we could make h be 1. So we just come to this point 3. So let's put h1. So move on to the points. Sorry, it's jumping. Move along to the point f equals 3 here. At this point, the function is 13. So here it's gone up from 5 to 13, so it's gone up by 8. And it's gone up by 1, so the gradient is 8. And that's a drawing of that. So it's getting a bit better. So instead of going to this point, we're going just to this point. So gradient 8 is a better approximation than the previous one of 12. But again, it's still an overestimate. So I've done this calculation again, I've got 8. It's still good. Now, as I showed the visualizations, what you want to do is just reduce this value of h. So instead of going all the way to 3, we can just go to from 2 and increase by a half. So that's increasing from 2 to 2.5. Do the calculation for the gradients and I get 6. Okay. By dividing this by this, I get 6. But I can make it better. Instead of a half, I can go along to maybe just a fifth step of 0.2. So it's just going from 2 to 2.2. And then if I do that, if I subtract the value at 2.2 from the value at 2, divide by 0.2, I find the gradient is 4.8. So now I'm getting really close. But I can go further with the power of computers. Do a tenth, I'm getting 4.4. Do a hundredth, there's no limit to what the computer can do. So that's from 2 to 2.01. Even a thousandth, from 2 to 2.001. Very, very accurate. With the naked eye, you can't tell the difference. So it's excellent, very precise. But we're not interested in approximation. We want precise answer. So all we do is we simply instruct the computer to take a step of 0. And it goes, and here we have the exact answer. Except now we have our first meeting of the dreadful pink text. And pink in Maple means that there's an error, it can't do it. So even the computer can't divide by 0. So it's actually, using this method is impossible to get the exact answer because we need a step size of 0, but then that becomes undefined at this point where h is 0. Now this puzzled people a great deal, and in the 1600s, both of these people, Leibniz in Germany and Newton in the UK, were really puzzled over this because they were trying to solve various practical problems. And they found a solution pretty much at the same time, and Germany and the UK have argued about who was first and whether they copied each other and so on, whether it was plagiarism. But we'll leave that to one side. What you can do is you can use the stuff that we did yesterday, the basic maths, to overcome this problem. So if we take what we've been working with here, put in, I replaced the a by the x because we're supposed to use the x really in the function, and the function f is this. If you take this and put in a is x, so a plus h is x plus h, then you have this. So at the point where x is equal to a plus h, then the function has this part here. That's the function at the point x is equal to x plus h is there. That's that first part. And then you subtract this part here, which is the original height of the function, which is this part. So that gives you the rise, how much is increased, and then you divide by h. And here we can't do it because h we want to be tiny, and in fact we want h to be 0, which is impossible. So just for a moment we forget the fact that this is all impossible and not defined, and just imagine that we can carry on as though there was reality here. So if we expand the top row using what you did yesterday, you'd find this. You should be able to check that by hand. It comes out to this. So notice that when you expand the brackets and subtract it, it simplifies a lot. You subtract like terms and so on. And now you have this. But now, through suspending that problem of it being not defined here, we can now just cancel out the h's. So that goes with that. This goes with this. This goes with this. Cancel out the h's. We have this. And now suddenly the problem has disappeared. Here we can put h is 0, because it's no longer on the bottom of a fraction. H is 0 means this disappears, and we get the answer that Leibniz and Newton had all those years ago, which is that we can get an exact answer, which is 8x minus 12. Then we remember, okay, we're interested in the point x is equal to 2, so we put x is 2 here. 8 times 2 is 16, minus 12 is 4. So the precise slope, the exact slope there is 4, which is what we can see we're getting closer and closer to. but now we can beam in on an exact answer and get a 4. Also, as a byproduct, we've got this, which can tell us the gradients anyway, so this is the derivative function. So when you find the derivative of the original function, this one, this is the derivative function, which gives us, well, that's the derivative of this original function here. Of course, in real life there are simple rules to do that. Maybe we can do it automatically. This command diff automatically differentiates the function to give you that, and then the command putting a big D and then the function in brackets does the same thing, defines the function as a derivative. And then into that you can then say, okay, if that's defined as a derivative, then substitute into, and you get the answer 4. Okay. So that's how it works in first principles. There's a few simple rules for doing this, so if you have not followed all these above details, that's fine. The next part is the part you really must know how to do, just applying simple rules, and it's a lot simpler. So we'll go on to that in the next video, but here just a reminder of the process. So we've got this, and what happens, you click on this and there you get some commands where you can just play it. So it gets smaller and smaller, and then we get to this point here. Alternatively, just to show that it works elsewhere as well, if I put into that derivative function, which remember is this function here, into this function here, if I put in the value x is -1, I find the value of -20. Well, that's because we're looking at the gradients here, and we can see what the equivalent process would be using this animation. So what you're doing there is predicting what's that exact gradient going to be there, and that turns out to be -20 because it's highly negative. Okay. So that's the idea from first principles. In the next video we'll go on to the essential stuff, which is the simple rules for finding the derivatives of simple functions. So thanks for watching, and I'll see you in the next lecture.